this video, we will talk about the sample variance, that why we divide n minus 1 with in a sample variance. This question is asked in a data science interview, why we divide n minus 1 in a sample variance, right? So let's understand this. Here is the population, right? Here is the population which is denoted by n, and the sample data is denoted by small n. So now we want to calculate the population mean. To calculate the population mean, we will use this formula, which is the summation of I to capital N xi, which is the observed values, divided by capital N. So that is how we calculate the population mean. And the sample mean, which is denoted by x bar, we calculate the summation of I to n small n, which is xi, which are the observed value, we divide with the small n. Similar to this, we calculate the variance of the population, the summation of I to capital N with the x minus mu, which is the population mean, whole square divided by the n. We calculate the population variance with this formula. Now, for the sample variance, there are two methods. The first one is a bias estimator. In a bias estimator, we do the summation of I to n in the x minus x bar whole square divided by n. This is n, small n. And the second formula is s square summation of I to small n x minus x bar whole square divided by n minus 1. So that is the important point. So why we divide n minus 1, why we use this formula, which is known as the unbiased estimator, and why it is known as the bias estimator, I will tell you in a while, right? So today's topic, we are going to discuss this point, the why we divide n minus 1, right? So when we use this. Now there are two cases we are going to discuss, right? There are two cases. In case 1, we have a population which are representing the age data set, and age represent. In this case, the data is present in a population in this way. Simple, you can see the spread, there is no skewed, there are simple data is present in this way. So we take the samples simply, right, and we calculate the sample means. We take the samples and we calculate the means, and when we compare this sample mean with the population mean, it is almost somewhere near to population means. In this case 1, not just population mean and sample mean are closer, but also when we calculate population variance and the small sample variance will be calculated with this formula, the bias estimator, right? And the population variance calculated with this formula. When we calculate this value, it will be almost similar in this case 1, right? Now, sometimes what happen in population, the data set is present in this way, where some skew data is present, right? Some skew data is present. Unluckily, what happened, we take those unskewed data set as a sample. So when we take this skewed data set as a sample, and we calculate this sample mean, there will be the difference between the population mean and sample mean in a case 2. Why there will be the difference in the population mean and sample mean? Just because of we take the sample which were skewed. Unfortunately, sometimes it happen, right? And if there is a difference between the sample mean and the population mean, obviously there will be the difference between the population variance and a sample variance in this case, if we use this formula. if we use this formula for the small sample variance and calculate the S, it will be very small compared to this, and there will be the huge difference. Obviously, why we calculate this with this formula, there will be the very small value of this S square, and there will be the huge difference between the population variance, which is the sigma square. You can see the huge difference. Here the difference is not, here the almost similar, but in case 2 there is a difference in the mean, there is a difference in a variance if we use this first one formula, right? So to tackle this problem or overcome this problem, scientists had made some correction, and that correction is known as the Bessel correction. This correction is known as the Bessel correction, right? This is the case 1 and this is case 2. In a case 2, what we did, we calculate the sample variance with this formula, and we see we use this formula, this value we got, is very small, and there is a huge. To tackle this, what we did, and Bessel correction did, it divide this formula, not just n, but divide n minus 1. In mathematics, if you divide any number with a big number, the value will be very small, right? So that the reason why, when they made so many experiments, they divided with n minus 1, with n minus 2, with n minus 3, but in the end they have seen when we are dividing with n minus 1 and calculating the sample variance, it gives little bit bigger value compared to this. When we calculate the sample variance with this formula, it will give a bigger value compared to this formula. So reason why we use this formula, and when we calculate sample variance with this formula, the difference is very small. Here you can see the difference is very small compared to this. When we calculated the sample variance with this formula, the difference was very huge in case 2, right? Because sometimes what happens in a population, from the population we take the samples, right? We take the samples. Sometimes what happens, the data is present in this way, very simple way, there is no skewed, but there is a possibility the data is present in this way. Some point the data is skewed means at a one point the data is present, so many data is present, very very compressed data is present here, and due to this reason, and when we unfortunately take this skewed data set as a sample, there will be differences in a mean, right? Because mean is shows the central location obviously of the central location of this will be here. There is so difference between the population mean and sample means. Similar to this, when we calculate this population variance and the sample variance, there is a huge difference, right? When we were calculating with this formula on a sample variance. So after this, they made corrections. They used this formula, right? They divided with the n minus 1 because data was present in a skew, and just because of skew, there was no variation in a data set, and it gives the value. If you are using this, it will give the value very small. Reason why we use this formula and divided the n minus 1. When we divided the n minus 1, it was gives a little bit bigger value compared to this. So reason why we use this formula where we calculate the sample variance, and it is known as, reason why it is known as unbiased estimator, because when we were using this, it will underestimating the true variance, right? because population variance was huge, and it was this formula was giving very small value. So that is why we use this formula, which is known as the unbiased estimator, because it gives almost not equal but almost similar to the true variance. And the reason why it is known as unbiased estimator, and this is known as the biased estimator.